that should look like a copy myself. Oh, but we're not taking it. That's for you. That's for you. For you guys to study. Yeah, we're not taking. You guys took that quiz yesterday. I'm just handing you a blank copy of it for your edification and studying, I guess. Let's see here. Let me begin with a word of prayer. We'll dive right into it. So I get this thing clipped on me before I forget. Heavenly Father, we thank you for this day again. I thank you for this class, and we thank you for your creation, that we can understand it. Help us to understand a little bit more about integration today. And I pray that the students will be encouraged if they're struggling, just to do their best, Lord, for your glory, Lord. In your name I pray, Lord Jesus. Amen. So here's the exciting attendance sheet. So I'll let you start it. There you go. So all right, so the first point of integration. So we're going to be focused on indefinite integration for a bit. Eventually we'll get back to definite integration. What's the difference between definite and indefinite integration? Well, indefinite integration, the answer is, technically speaking, a family of functions, right? So another way to say that is it's the most general antiderivative that we can offer. So sometimes that means something, a little bit sneaky. Like, for instance, the integral of 1 over x is not natural log of x, it's natural log of the absolute value of x. We need to put absolute value there just to take care of the case that x could be negative, So that's sometimes what I mean by when I say most general. I want the formula that covers the most cases. But generally speaking, it just means add a constant, because any two antiderivatives, since they share a derivative, as the derivative of the two antiderivatives is equal to the integrand of the function you're integrating, we know the two antiderivatives of a given integrand, they must be equal up to a constant shift, right? Excuse me. But what's the process of integration? All right, so basically this is it, definition. The integral of f of x dx is equal to, let's say g of x plus a constant, if and only if what? We need dg dx equal to what? Or maybe I should put y. Let me put y here for a second. Y is a function of x, right? That's only true if and only if dy dx is equal to f, right? So every time we're solving an antiderivative, an indefinite integral, right? Oh well. Technically speaking, we're solving a differential equation. You're like, wait a minute. I don't have to take differential equations yet, maybe ever. Well, I mean, that's kind of true, but it's kind of not. Because every time we integrate, we're solving that differential equation right there. dy dx equals to f. F is given, right? So typically here, this is given. Goal, find the y, right? So we know a bunch of cases already, right? So the first order of business is to write down what we already know. But I'm going to write it in a slightly surprising way. I'm going to write everything we already know, except instead of using the letter x, I'm going to use the letter u. Okay? So let's start out real basic. What's the integral of du? It is u plus a constant. What's the integral of u du? It is 1/2 u squared plus a constant. What's the integral of u squared du? It is 1/3 u cubed plus a constant. What's the integral of du over the square root of u? This one maybe you need to think about a little bit more, right? That's what? Think about this. We've got u to the minus 1/2. Yeah?
I was going to say 2/3 to x
Nope, you're thinking the square root. So it's minus 1/2. So we take minus 1/2, right? We add 1. So we have u to the minus 1/2 over minus 1/2 plus 1. What's minus 1/2 plus 1? Yeah, it's just 1/2. What's 1 over 1/2? 2, right? So what you got here is 2 times the square root of u plus a constant. All right, that's the antiderivative of 1 over the square root. Now the integral of square root of u to u is indeed 2/3 u to the 3/2 plus a constant. The integral of the cube root of u du is equal to, I take 1/3, I add 1. 1/3 plus 1 is 4/3. Dividing by 4/3 is the same as multiplication by 3/4. So I put 3/4 u to the 4/3 plus a constant. This marker is now dead. I think all my markers are dead. Man, it was close. I'll take it. So are we good on these? Let's keep going. What else is there? Well, you also got yourself integral of du over u is equal to the natural log, the absolute value of u plus a constant, right? What else do we know? Integral of a to the x dx is equal to, oops, my bad, my x's are showing here. Let's go back to u. So we've got a to the u divided by the natural log of a plus a constant, right? Special case of this, our favorite case, integral of e to the, man, I just really want to write x there, but e to the u du is equal to e to the u plus a constant. I'm gonna switch it up a bit here. Integral of sine of w dw, what's that? What's the integral of cosine of w dw? What's that? Negative cosine w plus constant, and then sine w plus a constant. What if I add an h to these? What's the integral of sinh h? Sinh h of, let's say, phi, d phi. What's the integral of cos phi, d phi? Bless you. So the answer is cos phi plus a constant, or sinh phi, because the derivative of cos and sinh is respectively sinh and cos, right? No plus or minuses here, thankfully. Even easier than sine and cosine. What else do we have? How about these? What is the integral of secant squared u du? What's the integral of secant u tangent u du? What's the integral of du over 1 plus u squared du? What's the integral of du over the square root of 1 minus u squared? Buying myself some time to move the camera. You guys will catch up. I'm walking slow today. By the way, if I was to give you guys a quiz tomorrow, and the quiz was just do these integrals, all right? You ought to be able to do that quiz in about 3 minutes flat. That's where you need to be. That's where you got to be by the end of this course. You need to be able to do these, like, reflexively. All right? Because you're going to need to know them for the next course, right? And if you don't know them reflexively, then it's going to hurt you there. In order to know these reflexively, what do you have to really be able to do? Practice them, but the deeper answer is you need to know differentiation, right? In order to undo, you must first be able to do, right? Differentiation is the opposite. So don't be the student on the final who is like integrating where you're supposed to be differentiating. You need to study enough that you get past that point. We're all at that point to start with, right? This confusion between the two processes, but you need to like find yourself some benchmarks so that you don't make that mistake. So the integral of secant squared is tangent, because the derivative of tangent is secant squared. This is secant u plus a constant. This here is inverse tangent of u plus a constant. This one is inverse sine of u plus a constant. Let's take a walk down memory lane and work out inverse hyperbolic tangent. I think I'm about 90% sure on it, but I'm not absolutely sure on it. Let me show you what I do when I forget. So we set y equal to inverse hyperbolic tangent of x. What do I do then? I take the tangent of both sides. So what I'm doing right now is I'm deriving the derivative of inverse hyperbolic tangent. All right? The derivative of tangent is what? Oh, I forgot that. How should I remember it? How do you rederive the derivative of tangent if you forget it? Remember, tangent is sinh over cosh. Use the quotient rule, right? And when you work through that, you'll see what you get is hyperbolic secant squared. So this gives us hyperbolic secant squared of y, dy dx by the chain rule equals to 1, which gives us dy dx is equal to 1 over hyperbolic secant squared. But remember, cosh squared y minus sinh squared y is equal to 1. So if I divide that by cosh squared, I get what? I get 1 minus hyperbolic tangent squared y is equal to hyperbolic secant squared y, because 1 over cosh is hyperbolic secant. So what do we have? We can rewrite 1 over secant squared as 1 over 1 minus tangent squared y, right? Which in this context is 1 over 1 minus x squared. All right? Now this only makes sense if x is actually in the range of hyperbolic tangent. And we work this out from a graphical perspective. The range of hyperbolic tangent is just minus 1 to 1. All right? So the integral I'm about to write has limited applicability. But for this context, for minus 1 less than x less than 1, we can write this. The integral of d, let me put a u here. Integral du over 1 minus u squared, guess what it's equal to? It's equal to inverse hyperbolic tangent of u plus a constant. How do I know that? I know that because everything I just worked out in blue. All right? Have I exhausted our list of things we know for basic derivatives? Maybe. There's a few others. Maybe you could look back up, right? Like, oh, we know cosecant and cotangent. We know those, right? Like, what's the integral of cosecant squared u du? What's the integral of cosecant u cotangent u du? What would those be equal to? Cotangent? All right, somebody check him on that, right? Let's check ourselves on this. And I believe, yeah, maybe this should be cosecant u. But are we right? Let's check it out. So to differentiate cosecant squared, how do we do it? Let's do theta instead of u, because I like my thetas better. Cosecant squared theta. My bad. I'm supposed to do what? Am I supposed to differentiate the integrand? No. What should I be differentiating to check my answer? The antiderivative, right? The integral. The cotangent, right? Whatever you want to call that. So what's the derivative of cotangent? Well, it's what? Cosine theta over sine theta. How do we differentiate that? Take a walk down memory lane here. Quotient rule. Derivative of the top is minus, so I get a minus sine squared theta, and then minus cosine squared theta from the derivative of the top times the bottom, minus the top times the derivative of the bottom. And then, of course, we have to divide by the denominator squared, also known as sine squared. Wait a minute, what is that? That's minus 1 over sine squared theta, right? Which is minus cosecant squared theta. So we were almost right. Almost right, right? What's wrong? We're just mention the negative. And I believe the same is true for this one right here. So you had watch out. There's some signs lurking here and there to be wary of. So suppose on a test you get the sign wrong. Am I going to take off like 30%? Kind of depends on the problem, maybe. If it's a bigger problem, probably just 10% though. We would like to get things correct though, you know? All right, I think that's pretty much it. I mean, the only thing I can think of is we did like derivatives of like inverse cosine, inverse hyperbolic cosine, inverse hyperbolic tangent. Oh, we did that one. So there's a few things there we could look up, right? But this is the usual like standard canon, if you will. Oh, one other thing I might add, because it just looks different, but it's good to know, right? Have it right on tap, so to speak. Like integral of du over u squared. What's that equal to? It's equal to, check this out, minus 1 over u plus a constant. If you doubt me, try differentiating the reciprocal function. What do you get? So we have the minus 1 power, we do the power rule, and so like, you know, I'll do it in x, but what's d dx of 1 over x? How do we think about that? That's d dx of x to the minus 1, which is minus 1 times x to the minus 1, which is minus 2, which is minus 1 over x squared, see? So the derivative of the reciprocal function is minus 1 over x squared. So if I'm integrating 1 over u squared, I put minus 1 over u, right? Because I know if I differentiate that, I'm going to get back. Or if you want to, you can just think of it, you know, many of these fall under what? The generic rule, we can always remember this, right? U to the n du equals to u to the n plus 1 over n plus 1 plus a constant. Now there's a string attached here for what? For n not equal to what? Oh, 0 is fine. Negative 1, yeah. In fact, 0 is a silly case, right? Integral of du equals to u plus a constant, right? I interviewed at a school once, and he told me a story about his advisor. And like after the first test in integration in calculus, he'd bring his grandson in, and he'd bring him up, and he'd say, he's like a 5-year-old, he'd be like, son, the integral of dx is what? And then the grandson would say, the integral of dx is x plus a constant, sir. And then he'd look at them and he'd go, even a 5-year-old knows this, why didn't you? Because, you know, on his test he'd had like integral of dx, and it just stumped a bunch of people, because it'll catch you off guard, right? Like, what do you do? How do you do integral of dx? What's that, you know? X plus a constant. I have no grandchildren, you're safe. All right, so you might wonder, why on earth am I spending all of this time going through all of these things that we've already talked about? It's not in my nature, is it? I don't usually circle back, do I? I tend to forge ahead, right? The reason I'm circling back and talking about all of this again is because these are the bedrock on which we must lay the foundation of the technique of u-substitution. U-substitution is only worthwhile if you know what you already know. So the whole technique of u-substitution is to take a new integral and put it back into one of these. All right? So let me show you. Example 1. Suppose I'm up against the integral of, say, x squared cosine of x cubed dx. All right? So what we're going to do is we're going to go, I don't know how to do that. That's not one of these, right? Or is it? If we let u equals to x cubed, right? Then, if we differentiate that, du dx is what? It's 3x squared, right? Okay, so then what I can do is I can solve this. This tells me that like dx is equal to du over 3x squared, right? Now you might not have known that you can do this, but you can. Now the justification for this ultimately is that it works. A more sophisticated way of saying that is that there's a theorem where the theorem basically says everything amounts to, you can treat du and dx like they're little bits of things, and you can cancel them like fractions, and it all works out. These things are in my notes, but we're just gonna forge ahead and do it. So I'm literally going to trade this dx for a du over 3x squared. So I got x squared, I've got my cosine of u, and I've got a du over 3x squared. Now for the u-substitution, to be successful, you must have eliminated all of the x's, all of the original variables. The only thing that must remain after the substitution is complete is your new variable, which I'm using u for here at the moment. So it's kind of weird to name a technique after the variable you use, but it's commonplace in calculus to call it u-substitution. A better term, a better label for this might be the substitution technique. That's really what it is. You don't have to use u. You could use another letter. The x squareds, they'd be canceling, and we got 1/3 cosine of u du. Oh, hey, now that is something we already know. What's the integral of cosine? Negative sign. So this is minus 1/3 sine of u plus a constant. And then nobody wants the answer in terms of the substitution. We need to go back to where we started. We need to undo the substitution for our final step here. So u is x cubed. So the answer is minus 1/3 sine of x cubed plus a constant. There you go. This is u-substitution. This we all need to learn, right? How many examples would you like to see of this? 5? Okay, I'll make it 30 then. So, example 2. We'll put a 5 in this example though. Integral of the sine of 5x dx. How about this? What should we let u equal to? U equal to 5x. du is equal to 5 dx. Oh, by the way, I'm going to start using a shortcut. I can write du is equal to du dx times dx. So that's what I do. I simply differentiate and multiply the derivative by dx. Du equals derivative times dx. We could have done that up here too, you know. Du would have been 3x squared dx. But anyway, let's go on. So I solve for dx. At the moment, that's the way we're doing things. There are other ways. You can do the algebra other ways. But here we'll solve for dx. Solving for dx is a method. We can use that. So we've got sine of u times du over 5, which is 1/5 what? What's the integral of sine? Negative cosine. So I got minus 1/5 cosine of u plus a constant going back to x. I've got minus 1/5 sine of 5x plus a constant. Now, I think that a good percentage of you could have guessed that. Did I do sine? Oh no. Why sine? Just to see if you guys are paying attention. You're welcome. See here. That's just good pedagogy. You got to make some. No. You make intentional mistakes for the students' learning, right? That's what you do. Of course, it was on purpose. Surely that must have been on purpose. A person who's done nothing but math their entire adult life wouldn't make such a mistake, right? Right. Thank you. So, point of order. Do I force you to write this u substitution down going forward? Nah. This one you can do in your head. But you need to do it, right? We can't just put, you know, minus cosine of 5x and hope to be correct, right? That chain rule of differentiation brings the 5 out. We have to cancel it with a fifth. Like, so the fifth is absolutely essential for the answer to be correct. Now, do you need to use u-substitution notation to prove this? I don't think so. I think you can do this in your head. All right. I certainly do these in my head in future courses, like I'm teaching Calc 2, Calc 3. I'm not going to show this. No, I'm just going to do it. Let's try something a little bit tougher. A wee bit harder. Example 3. Integral of tangent theta d theta. How are we going to do this? I think tea with honey beats a cough drop. Like, I'm coughing less today than yesterday, and it's not because I'm better. I assure you, I coughed violently on the bike ride in here. Tea with honey is better than coffee too, apparently. Our beloved math secretary is out for the day, so no one's made coffee. So any ideas, guys? What should we do here? Change tangent to sine over cosine. That sounds like a marvelous idea. And then what? That's where I take over, did you just say? So we got sine theta d theta over cosine theta, right? So this is a good place for me to introduce the other idea, which is that we don't have to solve for dx. We can also make like a substitution of, if you see some particular, you know, combination of symbols in the integrand, you can make a substitution for all of those symbols. You don't have to always solve for dx, or in this case for d theta. Like, let me show you what I mean. So like, if I let u equal to cosine of theta, then du is minus sine theta d theta, right? So in other words, sine theta d theta is what? It's minus du, right? So with respect to that substitution, I can just trade my sine theta d theta for what? Minus du. And my cosine theta? U, yeah? What's the integral of the reciprocal function, though? We talked about this, right? It's, oh, wait a minute, that's not the reciprocal. We talked about the integral, not the reciprocal function, but the what? Excuse me, I'm getting my story all mixed up. We talked about the integral of the square downstairs. That's different. This one, what's this? I should give you guys a pop quiz tomorrow. All of the basic integrals, you got a minute, you know? Do you guys have mad minutes when you're in elementary school? Some of you? Yeah? I love those things. I never won, though. There was another kid who always beat me and got the candy bar, which made me sad, because I wanted that candy bar. It did make me faster, though. Yeah? No? We're all friends here. You can guess. Okay.
See, I was thinking like you could bring the u up and then it'd be negative b and u to negative 1.
Okay, but what's the what's the problem with that? Like, what's the one case this doesn't work for is negative 1. Yeah. Yeah. That would be correct. Yeah, this is the natural log one. Natural log the absolute value of u plus a constant. So that gives us minus the natural log of the absolute value of cosine theta plus a constant. All right. And then most people don't leave the answer like that. We like to write this answer in the following way. See, this is natural log of the absolute value of cosine theta to the minus 1 power, right? By properties of log. What is 1 over the absolute value of cosine theta equal to? Well, that's also equal to the absolute value of 1 over cosine theta, right? Which is equal to the absolute value of secant theta. So the standard way to write this answer is the natural log of the absolute value of secant theta plus a constant. But honestly, folks, if you want to write it as minus the natural log of absolute value cosine, I am not bothered by that. I'm just telling you, people use this a lot. Okay? And this, every so often we hit an example where you really need to memorize the example and like remember it for future reference. This is one of those. All right? Like if you stumble upon a tangent, you need to know, oh, that's an integral we know how to do. This is how. Okay? Let's do another. Example 4. What if we're up against the integral of x times the square root of 3 plus x dx? How should we do this? By the way, there is a question you guys are eventually going to ask me. And the question you're going to eventually ask me is, how are you picking u? Yeah?
We guess u is 3 plus x inside square root.
Very good. You are correct. Now, I say you are correct because, you know, I have some experience and some memory, but the truth of the matter is you can make u whatever you want. The question is, does it work or not? All right? This one's going to work because that makes the radical less foreboding. Check this out. So for this one, du is equal to dx, so that's nice, right? I'm going to work down here because I worked myself into a corner, my bad. So I've got integral of x square root of u du. Great. Now what do I do? Couple different interpretations. One thing I do is throw my hands up in despair and say, I've got an x. This didn't work. Right? The other thing I might do, equally incorrect in some sense, is to just ignore the x and integrate square root of u du as if that's something you can do. No! You may not ignore the x. X and u are intertwined. They depend on each other. You can't just ignore the x, although that's a very popular move on the next test. Don't be that person. What should we do? What's the correct path here? Change x into u minus 3. Right. That is the thing to do. Solve for x. X is equal to u minus 3. So that is in fact equal to u minus 3 times the square root of u du, which then we can do by our usual means. That's u to the 3/2 minus 3 u to the 1/2 du. Integrate that thing. 3/2 plus 1 is 5/2. 5/2. 1 over 5/2 is 2/5. So I get 2/5. 2/5 u to the 5/2. Add 1 to 1/2, I get 3/2. 3/2 divided by 1 over 3/5. The reciprocal of 3/2 is 2/3. So 2/3 times. So I get minus 3 times 2/3 u to the 3/2 plus a constant. Uh-oh. This cough is slowing me down. I guess that's just as well. So the 3's cancel, right? And we don't want an answer in terms of u, so go back to what u is, 3 plus x, right? And here you go. The answer is 2/5, 3 plus x, or if you like x plus 3, to the 5/2 power, minus 2 3 plus x to the 3/2 power plus a constant. At this point, I'd just like to stop and appreciate for a second how amazing u-substitution is. Like, think about this. Could you have guessed that antiderivative we just calculated? In other words, if you ask the question, find me a function that when you differentiate it, it gives you back x times the square root of 3 plus x. Could you do that? Just from guessing? I don't think I can. But there it is. If you differentiate this thing somehow, through things canceling out and junk, the derivative of this works back out to that. It's kind of shocking, isn't it? So that's pretty neat. Let's do another. Oh man, these boards are a mess today. Uh-oh. Oh. How about example 5? What if we're up against, let us say, the integral of ax plus b to the 42nd power dx? Excuse me. Goodness gracious. What do you think we should do here? All right, yeah. Sounds like a good idea. Let's try it out. U equals ax plus b, then du is a dx. We're assuming a and b are constants here, right? So this one I think I'm going to solve for my dx. dx is 1 over a times du, right? And what are we up against then? U to the 42nd power times du over a. We can integrate that, right? So the integral is 1 over 43a u to the 43 plus a constant. And so there's the answer. 1 over 43a times ax plus b to the 43rd power plus a constant. Yay. That wasn't too bad, was it? Not really, I don't think. Example 6. What if we're up against like dx over, see, I'll do x dx over, let's say 5 minus x squared, for instance. Excuse me. I will say this, as a general rule of thumb, a lot of times if you've got a reciprocal function, making u equal to the denominator is something worth trying. All right? If you have a radical, making u equal to the inside of the radical is often a good thing to try. These don't work universally, but they're often good choices. So here we'll try, what are we going to try? Yeah, u equals to 5 minus x squared. That gives me du is minus 2x dx, which gives me that x dx is actually equal to minus du over 2. So I've got myself an integral of minus du over 2 all divided by, well, u. In other words, I've got minus 1 over 2 times the integral of du over u. All right? And how do you integrate that? u plus c? No. How about minus 1/2 natural log of the absolute value of u plus a constant, right? Because we've got the 1 over u function here. So natural log of the absolute value. But we want our answer in terms of x. So I have minus 1/2 natural log the absolute value of 5 minus x squared plus a constant. And there you go. We could write the answer just like that if you like. Now, this doesn't always work. Let's look at one where this doesn't work. This next one here is a little bit trickier, but we'll get through it together. Suppose we've got something like integral of dx over 4 plus 4x squared. Oh, man. Oh, well. It seemed hopeful. Now, if I let the denominator be u, what's the trouble? Why doesn't that work? What's the problem with the denominator being 4 plus 4x? Why is 4 plus 4x squared equals to u not going to work for us? What's the problem? So in the u substitution, we have to change both the integrand and the measure. We have to take care of both the expression we're integrating as well as the dx, right? So sure, I can make that 1 over u for the integrand, but the dx is still sitting there. And the way du and dx are related, if we make u equal to the denominator, it's not helpful to us, see, because I'll write it down. Like if I let u equals to 4 plus 4x squared, that makes my du 8x dx, right? I don't have that x in the expression to make the substitution, right? Like that doesn't work. All right? So what should I do?
Could you factor out 4 times the denominator and this 1 plus
Oh yeah. So this is 1 over 4 integral of dx over 1 plus x squared. Oh, I'm sorry. I'm a dummy. This is actually just what? 1/4 inverse tangent of x plus a constant, right? Did we even need to use substitution here? We did not. Okay, so beware of that. That can happen. Let me force the issue. Let me force the issue here. Example 8. What if we're up against the integral of dx over 1 plus 4x squared instead, like that? Then what would we do? I can't factor the 4 out anymore now, right? Not without creating a 4th, which wouldn't be helpful. But what do we know? What we do know, is, thought is that the integral of du over 1 plus u squared, well, that's inverse tangent of u plus a constant, right? So if I can make what I have into that pattern, then I can make a u substitution and we can all solve the integral together. What should I make u equal to? Not the denominator, but what? U equal to what? I want u squared to be equal to 4x squared, right? 4x squared is also what? It's 2x quantity squared, right? So I should let u equal to 2x. If I do that, then my du is 2 dx. So what I'm up against here is du over 2 divided by 1 plus u squared, which is, I can put the half out front, integral of du over 1 plus u squared, which of course is equal to 1/2 inverse tangent of u plus a constant, which, finishing blow here, 1/2 inverse tangent of 2x plus a constant. There you go. That's how we do this one. Does that make sense? Yep.
So say something like that pops up on the test or quiz. Do you have to show the work if we remember?
Yeah, you gotta show the work. Yeah.
What if we remember the answer? Kind of,
Yeah, you gotta show the work. Yeah. I might have instructions that say, like, make a u substitution to solve the following integral. Be sure to, show your u and your du. I have certainly done that kind of thing in the past, so you've reminded me I need to do this. Yes, thank you. But let's try something a little bit twisted. What if instead of that we have like integral of dx over, I don't know, 2 plus 3x squared? What do we do then? I mean, we know how to deal with 1 plus u squared, right? How can we convert that to 1 plus u squared? I think of it this way. I need to change that 2 into a 1. So the way to do that is to factor a 2 out. So this is really 1/2 the integral of dx over 1 plus 3x squared over 2. All right, so I factored the 2 out. 2 plus 3x squared, right? 2 plus 3x squared is equal to 2 times 1 plus 3 over 2x squared, right? Then what? I make a substitution, but it's not so nice and whole numbery. It's not so wholesome. I really want my u squared to be equal to 3x squared over 2, right? So if you look at that, u is going to be like x times the square root of 3 over 2 would be maybe a good substitution, right? Because then u squared is 3x squared over 2 with that substitution. If I do that, what's my du? Well, du is root 3 over 2 times dx. So if I solve that for dx, I've got dx is the square root of 2 over 3 du. And so I've got 1/2 the integral of 1 over 1 plus u squared times the square root of 2 over 3 du. Which gives me 1 over 2 square root of 2 over 3 inverse tangent of u plus a constant, and then go back to where we started. So the answer is 1/2 times the square root of 2 over 3 inverse tangent of x times root 3 over 2 plus a constant. So could I have guessed the answer? Could I memorize the answer for problem, example 8? Yeah, probably. Do I like your chances for memorizing the answer to example 9? I maybe, but I don't think that's a good use of your memory. I think it's much preferable to learn u substitution, to hone your algebra skills, because you need to do that anyway, and find a way to do this the same way I just did it, which is through derivation. Not memorization, derivation. You might be able to memorize your way through Calculus 1. It's conceivable. You will not be able to memorize your way through Calculus 2. There is no possible way to get through that course except to understand it. So why wait? Start trying to understand now. Don't try to memorize everything. Now, is memorization useful? Is it helpful? Absolutely. Does it have its place? Sure. Is it everything? No. And that's probably one of the worst things that's been done to you in your previous math education is many of you have been taught to memorize a little bit more than you should have probably. Well, I don't know. I haven't lived your life. I don't know what you did. Maybe you had lovely math teachers and you're just a bad person. I don't know. I'm just kidding. I'm just kidding. Math teachers are the worst. Let's see here. Not me, of course. Let's see here. But starting to look like I'm not going to get to 30 examples today. Yeah? I was just joking. I almost never get past 20. So example 10. Let's take a break from the algebra stuff for just a second and do something that's similar but weird. What if you have e to the x? Oh, let's do something really weird. Dx over e to the minus x plus e to the x. This one is harder. We have, okay, everything I've done up to this point today, I would say is kind of like entry level to moderate u-substitutions. To me, this is kind of advanced. How do you do this one? Well, I'll show you. Yeah? Okay. No? Idea? Oh, okay. How about this? First, I'll do some algebra. E to the x dx is over e to the x times e to the minus x plus e to the x, right? So I multiply the top and the bottom by e to the x. And what does that do for me? Well, that gets me e to the x dx over what? 1 plus e to the x quantity squared. Maybe you guys can tell me what to do now. If I give you the problem looking like this, it's no longer an expert u-substitution problem. It's a moderate one. It's become moderate at this point, in my opinion. What should you let u equal to? U equals e to the x. Very good. If we let u equals e to the x, then du is e to the x dx. So making that substitution, we have integral of du over 1 plus u squared, which of course is inverse tangent of u plus a constant, which is inverse tangent of e to the x plus a constant. Hooray! There it is. I mean, obviously, if you want a function that when you differentiate it, you get 1 over e to the minus x plus e to the x, clearly you should just differentiate inverse tangent of e to the x, right? No, it's not at all obvious, and yet that's what this derivation shows, right? I have to appreciate the method. It's very cool. Okay, by the way, like, who invented u-substitution? No one knows. It's ancient. Like, I mean, who did it? Like, probably Newton did it. Probably Leibniz did it. I wouldn't be surprised if it predates them, honestly. Anyway. Okay, so example 11. Let's get back to our quadratic stuff. How about this? Integral of dx over, I don't know, x squared plus 4x plus 10. All right. First of all right. Let me make us feel better about our day for a second here. Let me slap a 2x up here. Oh, yay! If the 2x is there, I just make u equal to x squared plus 4x plus 10. My du is 2x dx. This is just integral du over u, which is natural log absolute value of u plus a constant, which is the natural log of the absolute value of, I don't even need the absolute value, by the way, guys, because this quadratic is irreducible. So I can even drop the absolute value bars if you're so inclined. I haven't showed you that it's irreducible yet, but we'll feel the pain of that in my next example. All right, like, so if the 2x is there, lovely, we can just do that. But what if it's not? What if it's not? How does this go?
Hold on. In your previous equation, y is equal to 2x and not, or y is du equal to 2x and not 2x plus 4?
Aw, man. Let me fix this. Just a sec. Hold on a second, guys. That's a good question. And the answer is because I haven't done this yet. There we go. Thank you. I was trying to make that happen. You're right. If it was just x dx, actually it would be just as hard, in some sense even harder than example 12. Maybe example 13 will be that example, okay? So what do we do with this? See, because I can't just make u equal to the denominator, right? What's my favorite thing? What's the thing I keep coming back to that you guys like fight me, kicking and screaming? Yes, completing the square. So completing the square is how you do this. So x plus 2, quantity squared. I've added 4, right? I've added 4. So I only have 6 left. You can multiply that out, you'll get back to the original denominator. Now that kind of looks like an inverse tangent integral, but there's that pesky 6 there, isn't there? So we need to factor that out. So now we're kind of doing what we did in example 9. We're going to factor the 6 out. 1/6 integral dx over 1 plus 1/6 x plus 2 squared. And then what we're going to do is we're going to let u equals to x plus 2 divided by the square root of 6. See, because then u squared is what? 1/6 of x plus 2 squared, right? So that's the substitution I need to make in order to make the denominator have explicitly the form 1 plus u squared, which is our inverse tangent integral. So then what? Well, dx is what? du is dx over the square root of 6, which means my dx is actually root 6 times du. So what we got here is 1/6 integral of the square root of 6 du over 1 plus u squared, also known as 1 over the square root of 6 times the inverse tangent of u plus a constant, which is 1 over the square root of 6 times the inverse tangent of x plus 2 over the square root of 6 plus a constant. And that's how you do these. You got to complete the square. Eh? What do you think? That's a lot? Yeah, it's a lot. This one, I mean, this is by far the hardest one I've done today. Yeah. Yeah, question?
So on like on the test, is it going to be at this level?
Yeah, yes. There will be
Or just like 1 or 2?
1 or 2. Yeah. I mean, every one you can't do is this difficult, right? So, I mean, I don't know. I mean, it's hard for me to gauge. You can look at old tests and things. I am a creature of habit. I do ask some easier ones, you know. Like I usually ask this thing. This always stumps 60% of the class, this thing. And tangent theta, usually people, about 70% of the class usually gets tangent. It's hard to miss that one. It's kind of interesting, you know. The only true anecdote